If you want to know the exact boiling point or stability of a new molecule, the traditional method requires synthesizing it in a physical lab. This process requires raw materials, complex equipment, and time, meaning discovering new chemical properties is inherently expensive and slow. But there is a mathematical shortcut. Instead of physical testing, researchers can bypass the lab entirely and predict a molecule's behavior using pure computation derived directly from its geometric shape. Translating chemical properties into math removes the physical bottleneck. It allows chemists to test thousands of potential materials on a computer before a single drop of liquid is ever mixed. A major focus of this computational approach is a class of molecules called benzenoid hydrocarbons. These are flat, interconnected rings of carbon atoms that form hexagonal shapes, and they are incredibly important building blocks in both material science and environmental chemistry. One of the key properties scientists need to know about these benzenoids is their pi electronic energy. This specific metric determines the molecule's unique electronic stability, dictating how it will hold together under different chemical conditions. The challenge is figuring out if we can look at a complex hexagonal blueprint and extract a single mathematical value predicting its pi electronic energy. Finding that single predictive number allows for instant profiling. Scientists can feed a structure into a quantitative structure property relationship study, or QSPR, and calculate its stability without running a single physical experiment. To get that predictive number, we translate the molecule into chemical graph theory. It becomes a mathematical network where atoms are points, vertices, and bonds are lines, edges. In these grids, every atom connects to exactly 2 or 3 others. We call these vertex degrees. By tallying up these connections across the whole network, we can calculate a topological index. This is a mathematical formula that processes all the vertex degrees to produce a single, unique total score for the entire molecular structure. The highly complex three-dimensional structure of the physical benzenoid has now been translated into a computable mathematical blueprint. But standard topological formulas sometimes lack the sensitivity needed to distinguish subtle differences between similar molecules. Researchers needed a more precise mathematical tool to maximize predictive accuracy. The solution was a highly sensitive class of mathematical models called the exponential Gourava indices. By combining the vertex degrees and placing them into exponential equations, they capture much deeper structural information. To find the absolute best predictor, researchers set up a contest between 2 variations of these formulas. The first is the exponential sum connectivity index, or ESGO, which adds the adjacent vertex degrees together. The second is the exponential product connectivity index, or EPGO, which multiplies those vertex degrees instead. Researchers gathered a sample dataset of 30 different benzenoid hydrocarbons, ran both algorithms to calculate their index numbers, and compared those results against the molecule's actual, laboratory-tested stability. This test isolates exactly which mathematical operation, addition or multiplication, creates the absolute most optimized map of physical reality. These scatter plots show the sum connectivity index on the left and product connectivity index on the right, mapped against pi electronic energies. Data points align tightly with fit lines. The sum-based correlation hit 0.9996, the product-based hit 0.9997. Both models are highly accurate predictors. This is a plot comparing the 2 formulas against each other. The perfectly straight line of data points confirms a 1.0 linear correlation, meaning both indices process nearly identical structural information. Because both models perform so well on the surface, crowning a definitive winner requires looking past the broad correlation numbers and analyzing the slimmest margins of mathematical error. Researchers calculated a purely optimal mathematical baseline using a least squares fit procedure. Then, they compared the specific edge weight coefficients of both the sum and product models to see which one mathematically drifted closest to that optimal center. The exponential product connectivity index pulled ahead. With a lower standard error of 0.1675 and coefficients that aligned more precisely with the optimal baseline, the multiplication-based model proved to have superior statistical stability. With this specific algorithm verified, chemists now possess a highly stable digital tool. They can screen massive databases of hypothetical hexagonal compounds and quickly calculate their pi electronic energy without entering a laboratory. By identifying the optimal mathematical formula, chemical engineering replaces the slow process of physical trial and error with high-speed computational prediction. If you enjoyed this breakdown of chemical graph theory, please like this video and subscribe to the channel, and let us know in the comments what scientific topics we should cover next. We also want to recognize our sponsor for making this content possible. This video was brought to you by Synestic Systems LLC, founded by Shane Persinger. Thank you very much for watching, and we'll see you in the next one.